Welcome back to the channel. Today, we're kicking off a brand new series, Advanced Trigonometry. Before we jump in, a quick recommendation. If you haven't watched my Introduction to Calculus series yet, I highly suggest checking it out first. Why? Because we'll be building on several concepts we established there. But just like in my calculus videos, my goal remains the same: to make trigonometry as simple, visual, and intuitive as possible. So grab a notebook, and let's start with the absolute fundamentals. What's the simplest geometric shape out there? Setting circles aside, of course. It's the triangle, right? 3 vertices, 3 sides, and 3 interior angles. Let's focus on the angles for a second. If we draw a line through the top vertex that's parallel to the base, a neat geometric property emerges. The angles touching this top line match the angles at the bottom. Combine all 3, and they form a straight line. A half turn, or exactly 180 degrees. This proves a fundamental rule: the sum of interior angles in any triangle is always 180 degrees. Triangles come in different flavors. By sides, we have equilateral, all sides equal, all angles at 60 degrees. Isosceles, 2 equal sides, 2 equal angles. Scalene, everything is different. By angles, we have acute, all angles under 90 degrees. Right, exactly 190 degrees angle. Obtuse, one angle greater than 90 degrees. Sometimes they overlap. Take a right isosceles triangle. It has 190 degrees angle and 2 equal sides. Since the total must be 180 degrees, those remaining 2 angles must be 45 degrees each. Now let's focus on the star of the show, the right triangle. Forget about scale for a moment. It's the geometry that matters here. We mark the right angle with a small square, and our reference angle with the Greek letter theta. The 2 sides forming the 90 degrees angle are called legs. The one touching theta is the adjacent leg, the one across from it is the opposite leg, and the longest, slanted side is the hypotenuse. If we construct a square on each side, something magical happens. The area of the largest square equals the sum of the 2 smaller ones. Algebraically, this means that the sum of the squares of the 2 legs is equal to the square of the hypotenuse. This fundamental relationship is known as the Pythagorean theorem. It's named after the ancient Greek philosopher and mathematician Pythagoras, who lived all the way back in the 6th century BC. Let's see a classic example using a 3-4-5 triangle. If we square 3 and 4, their sum equals 5 squared, which gives us 9 plus 16 equals 25. Now let's define 3 core relationships that depend only on the angle theta, not the size of the triangle. Opposite over hypotenuse. Sine, how much the triangle reaches upward. Adjacent over hypotenuse. Cosine, how much the triangle reaches forward. Opposite over adjacent. Tangent, the slope or steepness of the hypotenuse. In trig, these functions don't measure physical length. They measure orientation. Let's put this into practice with a quick example. Consider a right isosceles triangle with a hypotenuse of 1 unit. Since both legs are equal, let's call their length x. Now apply the Pythagorean theorem. Combine the terms on the left. Divide both sides by 2. Take the square root of both sides. Finally, rationalize the fraction. So for a 45-degree angle, both sine and cosine equal square root of 2 over 2. Now unlock the ultimate tool in trigonometry, the unit circle. Place our right triangle inside a circle with a radius of 1. Notice how the hypotenuse matches the radius. Forget the triangle for a moment and focus on the point on the circumference. Its coordinates are simply the cosine and sine of the angle. Now add the tangent. Draw a line tangent to the circle at the point 1, 0. Extend the angle line until it intersects this tangent line. The y-coordinate of this intersection gives the value of the tangent. Set the angle to 0 degrees. Here, sine is 0, cosine is 1, and tangent is 0. Increase the angle up to 90 degrees. Sine becomes 1, and cosine becomes 0. Notice that the angle line is now parallel to the tangent line. They never intersect, which makes the tangent of 90 degrees undefined. Push the angle further into the second quadrant up to 135 degrees, which is the mirror image of the 45-degree angle. The absolute values stay the same, but pay attention to the signs. Cosine is now negative because x is less than 0. Sine remains positive because y is greater than 0. Sweep through 225 and 315 degrees. Notice how the signs of sine and cosine change across all 4 quadrants. And what about the tangent? The sign depends on where the angle line intersects the tangent line at the point 1, 0. Mastering the unit circle gives you full control over trigonometric ratios. But what happens when we unwrap this circular motion over time? In the next video, turn these coordinates into continuous waves as we explore trigonometric graphs. If this visual approach helped you, hit the like button and subscribe. Drop any questions in the comments below. Keep thinking, keep exploring, and I'll see you in the next lesson.